Hello, my name is Fabian Cuétara Guadarrama. I work in Ernesto Rivera's research group at the Institute of Research in Materials of the National Autonomous University of Mexico in Mexico City. The title of my poster is Photoluminescent Hydrogels Containing Porphyrin Units, Mechanical and Fluorescent Properties. Hydrogels are 3D polymeric networks with high water absorption, finding applications in drug delivery, wound healing, diagnostics, and environmental remediation. We synthesize hydrogels with photoluminescent sensing properties for potential photodynamic therapy applications using frontal polymerization. The hydrogels were prepared by combining ethylene glycol acrylates with methacrylate-derived porphyrin chromophores. Mechanical properties were evaluated through compression tests, and singlet oxygen production in aqueous medium was evaluated by UV-vis experiments with ABDA probe. Incorporating chromophores into the hydrophilic hydrogel network overcomes their low water solubility. These materials open new prospects for advancing photoluminescent hydrogels with promising biomedical applications. Hydrogels are 3D networks formed through physical entanglement and non-covalent interactions, possessing viscoelastic properties that allow them to immobilize aqueous liquids. Photoluminescent hydrogels are used in photoelectronics, biomedicine, sensors, and actuators. They are fabricated by conjugating chromophores to hydrogelators or by physically loading them into hydrogel matrices. Frontal polymerization is a self-sustaining process where a hot polymerization front propagates through a monomeric medium initiated by an external energy source, such as heat, light, or others. It requires a high temperature to ensure self-sustaining propagation of the front until all the monomers are converted. Porphyrins, microcyclic compounds, are applied in energy conversion, optoelectronics, photodynamic therapy, PDT, drug delivery, and environmental monitoring. In PDT, they act as photosensitizers that generate cytotoxic reactive oxygen species, ROS, upon light absorption and molecular oxygen presence, with the first FDA-approved PDT photosensitizers introduced 3 decades ago and continues to advance. The goal of the project: porphyrin chromophores often lack water solubility, limiting their biomedical applications, especially in PDT for cancer treatment. Hydrogels offer a promising solution due to their compatibility. The goal of this project is to apply an efficient and rapid methodology for producing hydrogels incorporated with a chosen chromophore. In our research group, we have introduced porphyrin and pyrene into hydrogels. The incorporation of porphyrin photosensitizers, known for their singlet oxygen generation properties, is crucial for enhancing the effectiveness of PDT. Solid hydrogels, with their excellent biocompatibility, mechanical properties, and water swelling capabilities, are ideal candidates for PDT applications. First, we synthesize the porphyrin acrylate monomer, ensuring purification and chemical characterization at each stage. Hydrogels were obtained by frontal polymerization, where we first remove the stabilizing agents from the ethylene glycol acrylate monomers and thoroughly mix them with the porphyrin acrylate monomer. For this step, we did not use any solvent and we used only the necessary heating using a soldering iron to initiate a propagating polymerization front. After isolating the produced hydrogels, we cut them in small discs for characterization and further testing. Swelling measurements were performed by weight difference at specific time intervals in distilled water at 25 degrees Celsius. We evaluated their swelling response at different temperatures. We assessed the mechanical resistance through compression tests. Finally, we measured the capability of singlet oxygen generation by recording the UV-vis spectra of the ABDA probe at specific intervals of irradiation, observing the decrease in intensity of the maximum absorption band. The synthesis of the porphyrin methacrylate monomer began with the construction of the tetraphenylporphyrin macrocycle, TPPOH, which was then isolated and purified. Next, TPPOH reacts with the tetraethylene glycol bromide, and the resulting product was purified before reacting with methacrylate chloride to obtain the final tetraethylglycol methacrylate porphyrin monomer, TPPMA. Frontal polymerization synthesis was performed by mixing the TPPMA monomer with different amounts of ethylene glycol ethyl and methyl ether acrylates, PEG MEA and DEG-EEA respectively. The initiator used was aliquot 336 persulfate, and no solvent was required. The present work deals with the hydrogel prepared with 10% weight PEG-MEA and 90% weight DEG-EEA. Figure 1a illustrates a schematic of frontal polymerization. The monomer solution was heated using a soldering iron with 2K thermocouples placed 1 cm apart under the heating zone. Once the front was detected, we recorded a temperature profile shown in Figure 1b, and the resulting hydrogels incorporated TPPMA, which exhibited fluorescence when viewed under a handheld UV lamp as depicted in Figure 1c. The swelling response of hydrogels containing 0 to 0.4% weight TPPMA was evaluated. Figure 2a shows that incorporating TPPMA altered the swelling behavior compared to the blank copolymer matrix. Additionally, the hydrogels exhibited thermoresponsive behavior at 35 degrees Celsius. Their swelling capacity significantly decreased as illustrated in Figure 2b. Compression tests were performed to evaluate the resistance of the prepared hydrogels in both dry and swollen states, with 3 measurements taken for each experiment. Generally, the dry hydrogels demonstrated remarkable resistance to compression, while the swollen hydrogels exhibited different behavior, showing material rupture when compressed. In this experiment, we generated reactive oxygen species from PD10 hydrogels using 9,10-anthracene-diol bismethylene dimalonic acid ABDA as a UV-vis probe. In panel A, it can be seen that PD10 hydrogel in an ABDA aqueous solution, while panel B shows a blank PD10 hydrogel without TPPMA in the same solution. The tests were conducted at room temperature using a handheld LED lamp for irradiation at 5-minute intervals. The inset displays the absorbance values at maximum absorption wavelength. Result analysis and conclusions. The hydrogels prepared by frontal polymerization successfully incorporated porphyrin methacrylate monomer. Their swelling properties were evaluated, revealing a diminishing swelling response of almost 200% within the temperature range of 25 to 35% degrees. Dry hydrogel exhibited greater resistance to compression than in the swollen state, likely due to the expansion of the polymeric nerve upon swelling. Additionally, the hydrogels show ROS generation capability, as evidenced by the diminishing UV-vis absorption of ABDA. This effect was more pronounced in hydrogels containing TPPMA compared to blank hydrogel. The presented polymer materials exhibit good mechanical resistance, swelling capabilities, and ROS generation ability, making them promising candidates for future PDT applications. I would like to thank UNAM, PAPIT Project, and CONACYT for their financial support. And thank you for your attention. I'm open to questions. Bye.